So today's bit here is going to be talking about continuing on from our momentum post lab, and then also talking about some really great connections back to last unit. Again, what I've said before, if you understand these connections, momentum should be a very easy unit, and that's why we can wrap this up very quickly. So you'll see our first target is understanding those connections. We are going to connect to main ideas. If you can do this, like I said, it's an easy way if you understood energy to understand momentum. Second thing today is talking about momentum bar charts. Momentum bar charts are very similar to LOL diagrams. We'll talk about the similarities and differences and how we are going to use those. Number three, I can solve conservation of momentum problems. We're going to try a problem together. And of course, number four, you'll see this word impulse. We'll talk about how impulse is very similar to work. So for number one, let's take a look at number one. I can connect main ideas between energy and momentum. So we have this idea of energy, and we have this idea of momentum. And again, you will see that they are very similar in nature. First off, we have conservation. Conservation fits for both of them. So right away, if you understand there's conservation here, there's also conservation on over here with momentum. So if you understood conservation of energy, you should easily be able to understand conservation of momentum. Second part of this is the good old LOL diagram. Remember, in the LOL diagram, the circle is the system, and of course we have the two bar graphs. This was usually at some point initial, and this was our final. Well, you will note over in our momentum side, we will have something very similar. We're going to have what we call a momentum bar chart. And of course, what we're going to have is we're going to have bar charts here, but you'll notice they're set up a little bit differently. They're not really an LOL diagram. It's a little bit different because there has to be a positive and a negative side to the bar chart. Why is this? Because again, we said momentum can be negative, so we need to be able to represent if a car has negative momentum or positive momentum. So the way that we're going to represent this, let's say if we had cart A and cart B, for example, if cart A was moving to the right, it would have positive momentum because the velocity is positive, and we would represent it with a bar going to the right. If car B was moving to the left, we would represent this with negative momentum, and of course representing it with some negative, being negative on our momentum bar chart. The other thing that gets a little bit different with one of these momentum bar charts is if two carts collide. So for instance, if they collide and stick together. So for instance, if we have two carts going at each other, here's A and here is B, and they collide and they stick together moving to the right, the way that we're going to represent this is now they are together moving as one, so they share that momentum. So what we would do is we would draw a bar in here representing, hey, they have collided and stuck together. This is going into both of them, and they're moving to the right in this case, so you'd be able to see it like this. Of course, if we select our system the right way, you will see the total amount here should equal the total here. So you'll start to notice that means if this was 3 bars, this would have to be, in this case, let me draw this a little bit better, 4 bars over, so that 4 plus a negative 3 would give us plus 1 bar. That means on over here, guess what? We should have plus 1 bar. Let me make this. So that means both of these should share a momentum, and we'll talk about how you can run that calculation on over here. So again, conservation still fits. You can see the conservation happening on over here. The only difference is now we have negative momentums that need to be represented on our bar graph. The last connection that we can really make is going to be the idea of work. If you guys remember correctly, work was a transfer of energy. Usually we made our system so that we would look at this as a transfer of energy into the system. We took that object out. On over in our momentum side, we have this idea of impulse. Impulse is going to be a change in momentum. So the idea of a change in momentum means we have an impulse, just like work means a transfer energy or a change in energy. And so that means in our bar graphs, will momentum be conserved if we have impulse? No, we will see a different amount of momentum in the initial and final, which means we have a change in momentum. So, going back to our targets, you've just seen that we connect main ideas between energy and momentum. We can start to see those relations. And of course, number 2, how do momentum bar charts work together? We could see how we could do that very easily there. So, number 1 and number 2, let's take a look at number 3, looking at an example of a momentum problem. So, in order to do this, we need to have an example. We're going to go back to the lab. And I think the best example that we can look at is 2 carts. Look at the wheel on that cart. That's a little poor, but we're going to go with it. We have cart A and cart B sitting here at rest initially. So we know the mass of A, we're going to make this easy, is 1 kilogram. The mass of B is going to be 2 kilograms. And they are at rest. Then an explosion occurs, and you will see that cart A goes off in one direction and cart B goes off in another. So we see before the collision and after the collision, very similar to what we talked about in class. And we also see that A, let's have it traveling at a velocity of 2 meters per second. Now the question is, what is the velocity of cart B? So the way that we can do this is by setting up the good old momentum bar charts. So on over here, we're going to set this thing up where we do not an LOL, I guess an upside down tot. And what we are going to choose in our system, because there's no force given to us or anything else like that, we're going to choose our system so that we have conservation of momentum. So we're going to have cart A up here and cart B over here. So initially, before the collision, remember we always look at before a collision and after a collision. Before the collision, A has 0 momentum because it has 0 velocity, and B has 0 momentum. So we look at this, again, if you want, you can even run the calculation. PA, which is momentum of A, is M times V, MA times V of A. And we see that this would be 1 kilogram times 0 meters per second. So very easy calculation, you get a 0 there. Same thing with B. Now, in the after state, you will see that A is traveling with a velocity, which I guess would be a negative 2 meters per second because it is going to the left. So if we wanted to, we could calculate PA final in this case, which would be the mass of A, which is 1 kilogram, times the velocity of A, which is negative 2 meters per second. When we run this calculation, we'll get a negative 2 kilogram meter per second. By the way, that is our unit of momentum. So kilogram meter per second, we just leave it as is. It does not simplify down to anything. And we get A as being negative 2. So we can set this thing up. I usually like to write it on over here. That's a negative 2 bar representing our momentum. And because of what our diagram looks like, I now know what B's momentum should be. Because in the before state, my total momentum is 0. So that means in my after state, if I have negative 2 here, that means B has to have a positive 2 momentum in order for the total momentum to still be 0, in order for conservation of momentum to occur. So that means I know momentum of B must be 2 kilogram meter per second. And then what I can do is I can work that out on over here, and I can say, okay, that is the mass of B times the velocity of B. And so 2 kilogram meter per second is equal to the mass of B, which we have as 2 kilograms, and the velocity of B is what we're looking for, so we just divide out our 2 kilograms, divide out our 2 kilograms, and you'll notice that very nicely our kilograms will cancel, and I'm left with 2 divided by 2, which is 1 meter per second. So that is going to be our solution, and if I go back on over here, you'll notice that yes, the velocity should be 1 meter per second off to the right. So, going back, this is a nice example problem. We will try more of these problems in our worksheet tomorrow in class. And then last but not least is understanding the idea of impulse. Impulse, like I said, is very similar to work. And the way that we can talk about impulse is a change in momentum. So, to best understand this, we actually need to go back to the example of the two cars colliding. And during this collision, we had A and we had B on over here. During this collision, we had a certain force acting upon A. So we have So we have Fn going here. Wow, that is the longest N. That's a really weird, I don't even know how that happened. We have Fn here, Fg happening there, and of course we have Fn on A by B. And so what we can do is we can then go through and we can say, okay, well, the Fn on A by B is what is causing the acceleration. So what we can do is we can say that is equal to mass times acceleration. And as you guys remember in class, what we did was we made a substitution. We said Fn, or in this case, the outside force, is equal to mass times delta V over delta T. And if we wanted to simplify this out, what we can do is we can say this is mass times delta V, which is Vf minus Vi, all over delta T. And you start to realize that what we can do is we can actually simplify this down. And you can start to see momentum start to appear. M times Vf minus M times Vi all over delta T is what we have on over here. And remember, we still have F. This is now what we can call an outside force, which is causing a change in momentum. And so what we can now write is F times delta T is equal to MVF, which is PF, and MVI, which is going to be PI. And so from here we have this idea of delta P is equal to this idea of F times delta T, keeping in mind that, okay, this is starting to make sense. Delta P is what we call a change in momentum. And a change in momentum is what we call impulse. And that is equal to F times delta T. So, in conclusion, a really easy way to understand impulse is by doing F times delta T, and this is going to easily be able to calculate the change in momentum or the impulse on a certain object. Note, just kind of taking a further look back, if we were to look at this, that is caused by an outside force. So if I were to really connect this to anything, I'm understanding that an outside force by an object is going to be what's causing a change in momentum. This usually only deals with one object. If you have more than one object, you usually don't run into that problem. So this concludes what we've talked about. Going back to our targets on over here, we can see that there is a connection between energy and momentum. We can see how we use momentum bar charts. We'll be using those every single example from here on out. Conservation of momentum problems, like I said, that's going to be the worksheet. And last but not least, I know and understand the idea of impulse. We'll probably talk a tad more about impulse in class tomorrow, because there is some other interesting ideas when you start choosing your system differently. Make sure you're ready for that tomorrow. Have a great day.